Okay, so in this course you should log in your hello.itk account. So you will see this, this is the student front page. So you'll see the course description and the team of tutors. So there are 10 tutors, and the one in green is the the head tutor. So you can contact him if there is any anomaly, exception handling. You can contact him. He is in fact here also, Pratik. Tutors will be responsible for grading your assessments, all assignments, exams, and so on. As I said, we have around 160 students. We can go up to 240. Even 240 will be, I think, fine, because we have enough lab space. Up to 240. Yeah, but beyond that, I won't allow. And then there is this FCH that you can read. If you click on that, you will see the policy of the course. So you can see the details here. Yeah, it's an ESO course, but this semester the participants are only from outside CSE. But the content should still be fine, because we only assume that you have done ESC 101 or the analogs. Okay, so if you have done ESC 101 with good grades, it should be enough to understand the TTS and algo also. Yeah, so important thing is that you should follow emails and hello.iitk, your account. Okay, all the assessments and your marks and grades will be shared there in your account as we progress. And you should read the first course handout there. So you will see all the detailed policies of the course. If you have any queries, you can ask me or Pratik. Just shortly, main points are that there will be programming assignment with some small weight. So the programming assignments you can solve either in the lab slot or in the hostels or wherever. I think there will be a portal for that, right? Gradescope. Yeah, so you can submit to the portal and then it will be checked automatically. So there is some weight for that. And related to that, there is a lab exam which will have a higher weight, which will be in April before the EndSem. Okay, so if you have not practiced the programming assignments, you will have obvious problems, because you have to solve harder questions in 3 hours in the lab then, in the lab exam. So be prepared for that by solving programming assignments. The other important components are, there are these quizzes, 4 quizzes, which I think I will be taking in the slot of Monday, 3 to 4 p.m. They will all be announced, of course. 1 hour quizzes each, and then midsem and endsem. Okay, so there are many assessments. None of them is too high. All of them are, most of them are around the same weight. So it is distributed throughout the course. So you have to remain awake the whole time. If you sleep in the beginning or middle or end, you will have problems. Okay, so try to be consistent in your performance. And the lab space is, it's there in the FCH. It is Diamond Shubli, I think 204H, that building, and Kadim Diwan building, the old CSE building, 111 lab. So if you are few students who attend, then KD 111 should be enough. It has 55 seats. If all of you attend, then the remaining have to go to DTJ. And for 1 hour, there will generally be a tutor present. So you can ask other questions also. Theory questions also can be asked in that 1 hour, but it's optional. So that's Monday. Today 2 to 5. Sorry, not today, but maybe after a week or so it will start. Yeah, and the quizzes will be here in L7. So that we'll announce whenever you have a quiz. They are spaced around every 3 weeks, 3 or 4 weeks. Okay, so yeah, let's start the topic. So before that, I thank the earlier professors who taught this course. So Professor Surinder and Raghunath. For creating the course content over the years. Yeah, as they have said before, the main requirement for this course, apart from ESC credits, is a fascination for solving puzzles. Okay, and a bit of analysis, mathematical analysis. So puzzles you have seen already in ESC and other courses, where you have to design algorithms and also implement them so that they solve a particular problem. You must be doing competitive programming, so here also you have to program by hook or by crook to solve a problem. What you don't do in those exercises is analysis. You don't really analyze two different methods to solve a problem. So as long as your program works for the given input or the test case, you are fine. So in this course, the additional thing will be that after you have created multiple versions of an algorithm or a solution, you have to also analyze and compare. Okay, so why is that important? So let's start that business. So what is a computer? Right, these days it is hard to answer in one sentence. 30 years ago it was easier to answer. Now almost every device seems to be a computer. So we'll not make a list of what is a computer and what is not. But generally they have these three features or these three components. So first is the processor, which sometimes is visible as a CPU, but in many cases nowadays it will be invisible, right? There will be no CPU. Like in a smartphone, you will not see any separate component for CPU. Everything is integrated in one plate. So, but there is a region which is still called microprocessor or processor. So, for this course, just assume that it does. The smallest unit is one instruction, and it takes around a nanosecond to execute an instruction. Okay, so let's say 10 to the minus 9 seconds to execute one machine instruction. Now this machine instruction may be something that is arithmetic, like adding two numbers or multiplying, but usually it is not. Machine instruction is something even more trivial. This is just picking one thing from a register and placing it in a different register, or adding one to one register. Okay, some very simple thing is one instruction, but complicated things are broken up into smaller things. So you have to do, it does many small things to get a big thing done, for example, adding two numbers. So it is important what is the smallest instruction time. So that usually you see in advertisements as gigahertz, right? So 1 GHz basically translates to a nanosecond of execution time. So this is consistent with your advertisements of computing power when you buy. So you should think of us, when we say our algorithm takes 10 steps, you can translate into seconds as 10 multiplied by 10 raised to minus 9 seconds. Right? So this is what, if you want to think in terms of seconds, this would be the translation. So second component is what we can call fast memory, which is traditionally called RAM. Right? So this is very fast because it is either in the same plate where you have in the same chip where you have the processor, or very close to it. Okay, so it is to access this, it takes minimal amount of time. It's the fastest possible memory you can access, or the processor can access. And this is around the same time. So 10 raised to minus 9 seconds to read a byte or a word. And yeah, this again corresponds to the same configuration in the advertisements you see, around 1 gigahertz. So instead of frequency, I'm measuring it in terms of actual time in seconds, but it's the same thing. And what is the third component? Can you guess? I mean, ideally, the processor and memory should be enough. Do you need any other thing in a computer? Sorry? Sorry? Bus. Yeah, bus are the wires connecting them. That is not very important. It's already covered in the seconds we have written. Storage? Yeah, so storage is what we can call slow memory. So which is the hard disk drive and the external devices you will put. So this can be significantly smaller to access. This is like a millisecond, 10 raised to minus 3 second to read a byte or a word. So why is that? Why is it so slow? Because it's not on the same chip. It is there is some mechanical device which controls it. Like in a hard disk, there is an arm which actually moves. Right? So I mean, when an arm moves, that speed is much slower than the speed of electrons. Right? So there is a significant difference, 10 raised to 6 times slower. So that's because of the mechanical component. I mean, it is electromechanical, but as soon as you have some mechanical component, it will drastically reduce the speed. So if it is so slow, what is the need for it in a computer? Why can't you put everything in RAM?
Processor might get confused.
No. Processor is too smart to get confused. It is just that the same amount of space you cannot create near the processor. And even if you create, again, the access and the buses are not very clear how to design that. I mean, it's an engineering constraint. The engineering currently doesn't allow that much of memory as HDD will allow. So to do that, you really need this mechanical system and something other than buses or small wires. So it has always been a problem. I mean, earlier days there was this floppy disk, there were magnetic tapes, and then there was CD, then CD became DVD, and so on, right? So that engineering has been improving, but it is not at the level of next to the processor. It's still something external, and mechanical devices have to be involved. It becomes slower. Also, if you try, I mean, these days you have bigger RAMs, but then they get more and more expensive, right? So if you want to store, let's say, the data of all the citizens of India in a RAM, then it will be very, very expensive device. So instead of making that, you would have to make it cheaper. And when you make it cheaper, then it becomes slower, right? So there are these engineering and economic constraints. So these are the three main components, and every other thing is just accessory to these devices. Okay, so yeah, you can see that each of these things is important. And now, where does the algorithm live? So what is an algorithm? So this course has two keywords, algorithms and data structure. So let's understand those two keywords. So where do you think algorithm lives amongst these three components of a computer? Yeah, so algorithm is more of an idea. It doesn't live in one place. It is what controls everything, right? But if you implement the algorithm as a C program, for example, then the C program will reside mostly in RAM, and the processor will read parts of it and follow that. It will implement whatever step, let's say in the C program, whatever step number 10 says, processor will execute that, then go to step 11 and step 12 and so on. Right, so algorithm is an idea. This is not a physical thing. It's just a recipe which all of these things will follow, and especially what the processor will read and command. So just to give a simple definition, it is a sequence of instructions. Fed to the computer. And since you have learned C programming, so that's the best example. It's a C program. So yeah, so algorithm is an idea, and these are the ideas which this course is made of. Okay, so in this course you will learn many kinds of ideas to solve problems, and I in the class will stop at that, but you will be forced to go much further. So you will be forced to write down those ideas or set of sequence of instructions in a more formal way, analyze it, improve it, and then at some stage express it as a C program, and then run on a computer and see the output. Okay, so you will have to work much harder than I will. And I think you will, so Prateek will allow C, right? Yeah, so you can also code in C++. But it's very similar, so I don't think there is much advantage. What you will not be allowed is, say the problem is to add two numbers and you just call a function which is already available in C. So you won't be allowed to do that. So when we say you implement something, you should implement it from scratch. Okay, you are not allowed to just call a function which somebody else has already implemented. Other than that, yeah, C is fine. So that's it's an algorithm, and there is a hypothesis in the world of computer science that anything that human beings do is ultimately an algorithm. Okay, so anything we do, at least using physical devices, can be simulated on a machine, can be simulated in, for example, C. Okay, so that's a long-standing conjecture or hypothesis. It's called the Church-Turing hypothesis, that every physical device is ultimately just running an algorithm. So when is an algorithm efficient? That's what this course is about. So this is an important keyword which you will see again and again. So it is hard to define what is efficient for now, but it will be easier to realize what is not efficient. Right? So let us see what is inefficient. So let's see a counter example. So suppose you write a C program which itself is short, but then when it is given a big input, the execution requires a very long sequence of instructions. Let us say 2 raised to 50 instructions. So do you think this, if a processor runs 2 raised to 50 instructions, will it be efficient or inefficient? Why is it inefficient? It is just a constant amount of instructions, finite amount of time. So to see this, you will need this nanosecond assumption, the model that we have of the processor. So let's see how much 2 raised to 50 instructions, how much time will they take, right? So this roughly translates to 2 raised to 50 multiplied by 10 raised to minus 9 seconds. And 2 raised to 50 is around 10 raised to 15. So you get around 10 raised to 6 seconds, which is more than 11 days actually. So, and 2 raised to 50 is these days in practice very, very small because you may just write a number with 50 bits, right? Just 0, 1, 0, 1, 50 times. And you may ask whether this number is prime, right? So this number that you have written, its value is around 2 raised to 50. Or you can play the same game with 100 bits. So say you are given 100 bits, and so the value is around 2 raised to 100. And if you run the high school algorithm for primality, it will require 2 raised to 50 steps. Okay, so it's very easy these days to give a computer an input and write a small C program which will require 2 raised to 50 instructions. So much of your competitive programming actually does that. It just looks at the test case and implements a kind of glorified brute force algorithm. So those algorithms will break down when it comes to this stage. Okay, so when actually there is an input which requires 2 raised to 50 instructions, then continuously the program will run for 11 days and still not stop. Right, and then you can see that when we increase this by a square, and then it will become years or thousands of years, right? So this is clearly inefficient because you won't even be alive to see the day when the answer comes, right? And this necessarily is the definition of inefficiency. You want to see the result in your lifetime, and that is not happening. So this should tell you what efficiency is. Yeah, and maybe we have to see more compelling examples. So are there such examples in reality? So we'll see many, you have already seen many examples. I will just recall those examples now in this new light. So primality is a very good example, but that algorithm, the algorithm actually also you have seen. But anyway, so a simpler example is that of computing the Fibonacci sequence. Or so this was given by an Italian trader named Fibonacci around 1200 AD. So it's a very old sequence. In those days, even the decimal representation was not very popular. They would use the Roman numbers, and in that notation, these would become very quickly, they will become so large that they cannot even be expressed in that system. Because if you remember, Roman system was a finite set. So first time the numbers became infinite was when decimal and binary numbers system was introduced. But the concept was already invented of these large numbers. Amongst Indian mathematicians also, Pingla was the one who gave a similar recurrence. There is a question called Pingla's question which leads to similar sequences, and this is much older. This is from 300 BC. So what is this sequence? So this sequence is simply given by Fn equal to fn minus 1 plus what? Fn minus 2. So the previous two numbers you add up and you will get the next one. Right, that's the sequence, and defining the boundary conditions are, so we say f0 is 0 and f1 is 1. So this is the sequence. You can see this example of this, so it's just grows like this and so on. Right, so how fast is this growing is the question here, right? As a function of n, how big is this value f of n? So this interestingly grows extremely fast. So prove it as a homework exercise. That fn is growing faster than root 5 plus 1 by 2 to the n, which is faster than 1.5 to the n. Okay, so which is, I mean, if you think of this as somewhat 2 raised to n, you can understand the growth, right? So for n equal to 100 already, it's like 2 raised to 100. It's growing very fast. So any algorithm whose complexity or which requires fn many steps is already requiring exponentially. So this expression is called, we'll call this exponential. So this is called exponential because this n, which is kind of your input, sits in the exponent. Okay, so this is why it is called exponential. So any algorithm which you write whose analysis gives this function means that it's a very inefficient algorithm, because with n this will be growing like almost like 2 raised to n, so it will have the same problem as before. As n becomes, I mean, even for realistic n, this algorithm is highly unrealistic. It will never stop. Right, so very simple sequences which appear in so many contexts have this problem, so you want to avoid this issue. Okay, so more concretely, suppose you are asked to write a program. So short form for that will be WAP. So write a C program which takes as input n and outputs the value of fn. Okay. So what is the first algorithm or C program that you can think of to solve this problem? Just a for loop, right? You can just do a for loop with I going from 0 to n. N is provided by the user, and then in the ith iteration you can just implement this addition. So let's analyze that idea. So let's call this iterate fib n function. So what it does is just a for loop. Yeah, let me shorten this, it's too long. So this is you set iterative fib I equal to the previous values which you have calculated and stored in an array. Okay, and then the for loop will go to I plus 1 and so on. Actually, this is unfortunate notation. It makes it look recursive. Let me not do that. So this F is simply an array here. So you just have to declare an array F with values with the locations n many, and obviously you know F0, F1, and beyond that whatever n is provided. This for loop will run around n iterations, and it will give you the value of, it will give you all the values from F0 to Fn. So F has n plus 1 elements. Is that clear? So this is the first thing you can do just by looking at the recurrence, just updating this array by a for loop. So how much time will it take? If you were to analyze this, how many steps does it take in terms of input n? So very roughly we can say it takes around n steps, right? So this, we can just record that it takes around, number of steps is around n. This is not quite correct because also one has to pay the price of addition. In every iteration there is also addition involved. So you have to count that also because the numbers are growing bigger and bigger. So addition also takes time. But yeah, so that is kind of hidden inside this. So it's n multiplied by the cost of addition. But if n grows very fast, then the dominating term really is n, right? So we can say that the algorithm is as efficient as n, as order n. We'll formalize these things, but let's just go through with this intuitive example. Another algorithm you can write is the recursive one. So recursive Fibonacci series computation or function. So here what we can do is instead of the array, we can now write down a subroutine or a function for f and call it again and again, call it twice, right? So when you want to calculate f of n, then you call the function f of n minus 1, it will give an answer. You call in, after that you call f of n minus 2, it will give an answer, then you add the two answers, right? So this is called a recursive algorithm. I'm sure you have done this in ESC 101 pretty early. So the snippet of the code here is if n is at least 2, then you return the value n minus for n minus 1 and for n minus 2 and add the 2, right? So this is just a one line snippet of a recursive algorithm. And obviously there are base cases, so that also you can write. So in that case you have to return, I think you just return n. So if n is 0 or 1, you can just return 0 or 1, whatever it is, and it will be the correct answer. So there is a base, there is this base case, and then there are these bigger cases which are reduced to smaller cases, right? This is the recursive trick. So this is the same function which is being called here, this function. It isn't an array in this case. You are actually calling the function itself. Now what is the number of steps here? That's a trickier question. What can you guess? How many steps? So this is a C program on your computer. How many steps will your computer run for when the user gives input n? Yeah, so the correct answer is 2 raised to n. Why is that? So the problem is that these two executions which you are doing, which you are calling, this red execution and the orange execution, these are independent executions. They are being done sequentially. So first you are computing n minus 1 and then you are computing n minus 2. So you are basically doubling in this one step. So whatever was the time taken to calculate f of n minus 1, you are doing it again, right? So the number of steps here is essentially f of n, which we have shown is more than 1.5 to the n. Okay, because if you do this properly, then the recurrence that you are getting is exactly the one that we had written here. So f of n is equal to f of n minus 1 plus f of n minus 2 for the number of steps also. So here is an example of algorithm which is very simple to write, and probably in practice you wouldn't see it if you are going up to n 10 or 20, it won't be visible. But if somebody gives n equal to 100 or n equal to 200 or n equal to 1000, then your program will actually won't be able to give an answer. It will be an infinite loop, because the number of steps is so high that it takes thousands of years to finish the calculation, right? So simple codes, they don't mean that they will stop. Even for simple codes, even for very simple inputs, may never stop, right? So you have to be careful with the analysis of what you have written, the algorithm that you have implemented. So the previous one is far better, that is around n steps. But if you blindly follow the recurrence and ask the computer to do it by recursion, then it will get stuck. I mean, it will keep calculating the same thing, essentially the same thing again and again. It is making too many copies when what it should have done is just stored things as it is computing in an array. So that essentially tells you both about algorithms and data structures. So the algorithmic mistake you are making here is that you are calling recursion and there is really no data structure, when what you should have done is created a data structure, the array f as in the first idea, and then store there. So storing there helps you to use these values in the future. So it's a better organized mechanism to store information. Yeah, so this creates a problem already. I mean, in a computer, you can store, you can take n to be long int, and then it's just impossible to do this. 64 bits. In fact, in this case, both these algorithms will fail. So if you take n, if the user gives n to be long int, that's around 64 bits. So the value of n is around 2 raised to 64. Then you can see that the second idea, it fails. I mean, it fails already for n equal to 100. But the first idea also fails when n is that big, right? Because it takes around n steps, and this 2 raised to 64 is too large. This again will fails, as in it will take you around a year to stop. So at least the first one will stop within a year. The second one won't ever stop. It goes into trillions of years and more. So yeah, so once you have this kind of a mathematical analysis, which looks, I mean, if you haven't seen this, it's a bit complicated. But it is needed when, as your input becomes bigger and bigger, this analysis is required. You have to do this a priori analysis, the theoretical analysis, to actually get an idea of how bad or good your algorithm is as the input increases. So this is how we will do it in this course. These are just baby steps for you to get warmed up. Okay, so let's modify this question. So both these ideas are very slow. or very inefficient. For such large n. Also, one thing you should note is that Fn itself is very big. To store. Because Fn is around 1.5 to the n, so when n is very large, you will need actually n many bits or n many digits to store f of n. So if your n is 2 raised to 64, you will require 2 raised to 64 digits, right? So that again is, I mean, you will need some big data storage to store this. So that's another problem. But that is not the biggest problem here. The biggest problem is really in terms of time. So a related question can be asked, what about calculating just a signature of this Fn? So let's ask Fn mod 2024. Okay, so this will be a small answer because modulo 2024 means that you divide by 2024 and give the remainder. So there are the remainder possibilities are only 0, 1, 2 and 2023. So there are very few possibilities. So answer is very small. So there is no problem with storage. Can you calculate this in an efficient way? Is there a fast way to calculate this? Even for n as big as I have set here, long int, which is around 2 raised to 64 value. Yeah, so modular arithmetic, so every addition, let's say, so idea 1 is obviously better. So in idea 1, now the addition will be mod 2024, that is fine. But still the number of steps is n. So number of steps is still 2 raised to 64. So this is still intractable in practice. So you have to come up with a third idea, which you have to do at home. Okay, so do this as an exercise. Come up with a third idea which actually calculates very fast Fn mod 2024. So that requires a different idea. So think about that. Let's move to a different kind of problem. So example 1 was this sequence of Fibonacci, and example 2 will be, let's take subset sum. So what is the problem of subset sum? So here you are given a set of numbers, an array of integers, and you have to, and you are also given an integer, let's say s. You have to answer the question whether there is a subset of the array whose sum is s. Okay, so as the name suggests, that's the problem. So again, write a program which takes as input array E of n integers and an integer s, and output should be subset B or subarray B such that the sum of these numbers in B exactly equals S. Okay, so this again is a very simple to state problem, and it is equally simple to present to a machine, right? You can just come up with 100 numbers. You can come up with an array with hundreds of integers and come up with some s randomly and then ask the computer that whether there is a subset of this array whose sum is this. So the question is, how do you solve it? What is the simplest idea to solve this? If this was a question in competitive programming, how will you solve this? You will just go over all the subsets, right? Will it help if you sort the array? How much will it help? I mean, you can sort the array, let's say the maximum is m and s is m by 2, right? Or s is maybe m minus 1. So still you have to look at all the values. Sorting will not help. I mean, immediately it's not clear how much it will help. It will just take care of some corner cases, but still the challenge is that these numbers which are given, you have to look at all possibilities. So essentially you have to look at all subsets, right? So the solution you give in competitive programming versions of this is you just go over exhaustively all the subsets and try to find one. And you are not doing too bad because there is no better algorithm known to date. Okay, this is one of those problems which is we don't know how to do any better. And if you knew how to do this any better, then there will be another million problems which will be solved efficiently. Okay, so this problem relates to another million problems which are of practical importance. And they are all tightly related. So if you solve one fast, others also can be solved fast. So this is a collection of very famous problems. So I'm showing you only one. Yes, so the ideas, there is a real dearth of ideas in this problem. So first is, of course, try all subsets B of A and check. So basically pick a subset B. I mean, think of this as a complicated for loop. For all subsets B of A, the step will be check whether the sum of B is S. Right? So it's a for loop, and the for loop has how many iterations? Trivially 2 raised to n. Right? The array was of length n, so the number of sub-arrays is 2 raised to n. So that's the number of steps. Is there a way to improve this 2 raised to n? N times 2 raised to n? Yeah, sure, it's even worse. No, I wanted you to improve it. Sure, that is fine. It's because there is a for loop of 2 raised to n, and then when you do the check, you are again summing up around n numbers. So it is at least n times 2 raised to n. But is there a way to improve this? In fact, in competitive programming, you do improve this. There is a slightly faster way. Yeah, you can use whatever, but what will be the complexity that you will get over 2 raised to n? No, n square is fraud. As I said, this we don't know how to solve this fast. It's an open problem. S. Okay. Okay, you are assuming that S is small because S itself can be very big. S is a number. So as I said, if I give you a 100-digit number or 100-bit number, its value is 2 raised to 100. So that itself is very big. But yeah, if S was very small, sure, you can then do some other tricks. No, but just simple modification here can be that you don't go over all subsets, you only go over subsets which are of size n by 2 or less. I mean, you can do a trick there. So you can make it slightly better to 2 raised to n by 2. Since we are out of time, let's just leave at that. So make it n times 2 raised to n by 2. So you can do square root of this. Basically you do the for loop over subsets of size n by 2 or less. And there you can store the values. For every n by 2 sized or less subset, what is the value? You can store those values, and then you can see whether two of them add up to S. Right? So a small trick can make it faster. Yeah, but you have to actually properly check this. So I think better if you do this as a homework exercise. And then even with this complexity, the problems are that when n is, let's say 100, you can see the time taken. So time required for this is 100 times 2 raised to 50 times 10 raised to minus 9 seconds, which comes out more than 3 years. Okay, so just 100 integers, which is so small, right? Just 100 integers are given, and you have to check whether some S is appearing as a subset sum. That already will require 3 years of constant computation. Right, and as I said, we don't know anything better. So there are problems for which, no matter how smart you are in this course, you will still fail. And you should just hope that I don't give you such problems in the exam. Right? So you cannot solve all the problems, but yeah, there are problems for which there are clever methods. So we'll present those methods as we go along in this course.